In our previous module on convective heat transfer, you recall that we talked about forced convection and free convection. In forced convection, the fluid is forced to move over a solid surface. That movement is caused by some type of external mechanical means. For example, in case of air, one may use a blower or a fan. Similarly, for liquids, one may use a stirrer or a pump. So one easy way to find out if a problem involves forced convection is that you should read that problem and see if there is a reference to a pump or a blower. Well, the formulas that are used in calculating convective heat transfer in case of forced convection involve Nusselt number, Reynolds number, and Prandtl number. And these numbers appear because we are going to use an empirical approach, that is, an approach based on experimental data. In the empirical approach, the experimental data is condensed into mathematical expressions that involve these dimensionless numbers. First, we will look at flow inside a pipe. So our objective will be to try to determine convective heat transfer when a liquid or air is flowing inside a pipe. Now there are three different categories that we can use. We can consider a flow condition involving laminar flow in a pipe. As fluid enters the pipe, there is an entry region, and then after that it was fully developed. So our first two expressions will be for the fully developed flow, and then the third expression will involve both the entry region and the fully developed flow. And if we have laminar flow in a pipe, then we may have a fully developed condition with constant surface temperature of the pipe. In this case, the formula is very simple. Nusselt number will equal 3.66. So if you were to find out the convective heat transfer coefficient, you will essentially substitute for Nusselt number H dc over K, and that will equal 3.66. So if you are given the characteristic dimension, which in this case will be the inside diameter of the pipe, and if you know the thermal conductivity of the fluid, then just substituting those values in this equation, you can find out the convective heat transfer coefficient. Another condition is of a fully developed flow with uniform surface heat flux. So in this case, Nusselt number will equal 4.36. Again, if we were to find out the convective heat transfer coefficient, then we can write H dc over K equals 4.36, and if we know the inside diameter of the pipe for characteristic dimension, and if we know the thermal conductivity of the fluid, then we can substitute those values and calculate the value for H. Note that in both these equations so far, the value of thermal conductivity of the fluid is obtained at the average fluid temperature. So we will call that T infinity. The other case is for both entry region and fully developed flow. So this time the expression is as follows. Nusselt number equals 1.86 in parentheses Reynolds number times Prandtl number times dc over L raised to power 0.33, and then in parentheses mu b or mu w raised to power 0.14. Now in this case, L is the length of the pipe, dc is again the characteristic dimension, which is the inside diameter, and all the physical properties, including the mu b, where mu b is the bulk, viscosity, all these properties are obtained at the average fluid temperature. and we call it T infinity. Now mu W is the viscosity at the wall condition. So at the wall of the solid pipe, it will have some surface temperature, which will be different from the average fluid temperature. So mu W is evaluated at the surface temperature of the wall. The second case is of what we call transition flow in a pipe. This is the condition where the Reynolds number is greater than 2100 but less than 10,000. Now in this case, the formula is a little more complicated. Nusselt number equals, and it'll be a ratio, so in the numerator we have F over 8 times Reynolds number minus 1000 times Prandtl number, and then in the denominator 1 plus 12.7 F over 8 raised to power 1 over 2 and Prandtl number raised to power 2 over 3 minus 1. And F is the friction factor. Now you will recall that previously when you studied fluid flow, you would have studied friction factor, and friction factor is obtained for smooth pipes. The formula is F equals 1 over 0.790 natural log of Reynolds number minus 1.64, and the entire quantity is squared. The third case is of turbulent flow in a pipe, and in this case the Reynolds number is greater than 10,000. The formula in this case is Nusselt number equals 0.023 times Reynolds number raised to power 0.8 times Prandtl number raised to power 0.33 times mu B over mu W raised to power 0.14. Again, in this case, the fluid properties are evaluated at the average fluid temperature, except the mu W, where mu W is evaluated, that's the viscosity, and that viscosity is obtained at the wall temperature. dC again is the inside diameter of the pipe. These expressions are useful for finding out convective heat transfer in case of air or for water. We just have to find the right properties and substitute those numbers in these equations. Those properties are obtained from tables which are given in the appendix of the textbook.